Imagine walking outside right now into the dark, quiet woods under a sky filled with twinkling stars. Far above your head, an invisible red giant star is silently rushing toward our solar system at extreme speed. It is not staying in its own neighborhood, and it is not going to turn away before it reaches our cosmic backyard. In fact, it is heading straight for the massive bubble of icy rocks that surrounds our sun and protects our world. If you want to uncover real space mysteries that sound like science fiction but are backed by genuine scientific facts, hit the subscribe button right now. Join our growing community of curious thinkers who love exploring the deepest secrets of our universe every single week. When we look up at the night sky from our backyards, everything seems calm, solid, and permanent. The stars look like fixed pinpricks of light stuck onto a giant velvet dome that turns slowly around our world every night. We grow up learning that our sun stays safely in its own neighborhood, floating through space with billions of miles of empty room on every side. We like to think of our solar system as an isolated island in a peaceful galactic ocean, completely shielded from the rest of the Milky Way. The reality of our universe is far more chaotic and energetic than most people ever realize in their everyday lives. Nothing in space ever stays completely still, and every single object is constantly moving in a giant cosmic dance. Our galaxy is a massive spinning disk containing hundreds of billions of stars, and each one is traveling along its own unique orbital path. Our sun is zooming through space at roughly 500,000 miles per hour, dragging Earth and all the other planets along with it like passengers on a giant ride. Because all these stars are traveling at different speeds and in different directions, they frequently pass close to one another over long stretches of time. If you imagine a busy highway with thousands of cars driving at different speeds without any painted lanes, you can visualize how stars move through space. Most of the time, the space between stars is so vast that they pass each other without any noticeable trouble. The distance between our sun and the nearest star system today, Alpha Centauri, is more than 24 trillion miles. That huge distance makes it feel like our solar system is an unshakable fortress that no other star could ever touch. For many decades, mainstream scientists believed that no outside star had ever entered our solar system since the planets formed 4.5 billion years ago. They assumed that our outer neighborhood had always remained completely silent, peaceful, and untouched by outside visitors. They figured that any star passing through our region of space would stay millions of miles away from our sun's gravitational boundary. That comforting idea began to crumble when astronomers started building ultra-precise space telescopes to track stellar movements across the galaxy. These modern instruments can measure the speed, direction, and distance of millions of stars with incredible accuracy. By running these orbital pathways backward through powerful computer simulations, scientists can replay the past history of our galaxy like a movie running in reverse. What they discovered was a dramatic historical event that completely changed our understanding of our solar system's fragile safety. About 70,000 years ago, an entire double-star system passed right through the outer edge of our solar system. It came closer to Earth than any other known star in human history, cutting directly through the giant sphere of icy rocks that orbits our sun. Earth survived a terrifyingly close cosmic flyby that could have triggered a massive shower of killer comets into the inner solar system. To understand how close this really was, we need to look at how our solar system is structured far beyond the planets we know best. Most people are familiar with the main planets in our solar system, starting with rocky worlds like Mercury, Venus, Earth, and Mars. Further out sit the giant gas planets Jupiter and Saturn, followed by the icy giants Uranus and Neptune. Beyond the orbit of Neptune lies the Kuiper Belt, a donut-shaped ring of icy objects and dwarf planets, including famous worlds like Pluto. While the Kuiper Belt seems like the outer edge of our solar system, it is actually just the inner gateway to a much larger cosmic structure. Surrounding our entire solar system is a giant spherical shell made of billions or even trillions of icy objects known as the Oort Cloud. The Oort Cloud acts like a massive protective shield surrounding our sun and all the planets, stretching out into the deep darkness of interstellar space. The outer edge of this icy shell extends more than 100,000 times farther from the sun than Earth is right now. That means the Oort Cloud reaches nearly halfway to the nearest neighbor star system we see in our night sky today. Because the Oort Cloud is located so incredibly far from our sun, the pull of the sun's gravity out there is extremely weak and delicate. The icy objects floating in the Oort Cloud are balanced on a gravitational knife edge, easily disturbed by any outside force that passes nearby. If a star passes through or even near this cloud, its gravity can pull icy rocks out of their gentle orbits and send them crashing through space. Some of those disturbed rocks get thrown out into the empty void between stars, never to return again. Other icy rocks get knocked inward, falling toward the inner solar system where Earth, Mars, Venus, and Mercury orbit the Sun. That means a single passing star can launch a delayed swarm of comets that head straight toward the planets where life exists. Did you know that our solar system was surrounded by such a massive cloud of icy comets floating out in deep space? Tell me in the comments if you have ever heard of the Oort Cloud before, and drop a quick like on this video if you love learning about deep space mysteries. The story of how scientists discovered this ancient star flyby reads like a high-stakes detective story set in deep space. Back in 2015, an astronomer named Eric Mamajek was analyzing data on stars located relatively close to our solar system. He noticed one faint star system, located about 20 light-years away in the constellation Monoceros, that behaved in a very strange way. The star was moving across our sky very slowly, but measurements showed it was moving away from us at an astonishing speed. When an object in space moves slowly across your field of view while moving rapidly away from you, it reveals a critical physical clue. It means that in the distant past, that object was located much closer to your location than it is today. Think of a car driving straight down a long, straight highway directly away from where you are standing on the sidewalk. The car looks like it is barely shifting left or right, but its distance from you is growing bigger every single second. This mysterious system was named Schultz's star after the German astronomer Ralph Dieter Schultz, who first identified its existence. Schultz's star is not a bright glowing sun like our own, but rather a small, dim, red dwarf star. A red dwarf star is much cooler, smaller, and fainter than our sun, producing only a tiny fraction of our sun's light and heat. This particular red dwarf star also carries a smaller companion object with it as it travels through space. Its companion is a brown dwarf, which is a strange celestial object bigger than Jupiter but not heavy enough to ignite nuclear fusion like a true star. Together, these two dark bodies form a binary star system traveling through the galaxy as a closely bound team. The primary red dwarf has only about 8% of the mass of our Sun, making it barely heavy enough to shine as a real star. Because both objects are so dim and faint, Schultz's star is completely invisible to the naked human eye from Earth today. Before scientists conducted detailed calculations on Schultz's star, they expected that passing stars would always stay far outside our solar system's borders. Mainstream astronomers believed that any stellar encounter would happen at safe distances of several light-years away from our Sun. They figured that the space surrounding our solar system was far too sparse and empty for an actual star to cross into our territory. The scientific consensus was that our inner and outer solar system had remained undisturbed since the age of the early Earth. When Eric Mamajek and his team ran thousands of computer simulations tracking the path of Schultz's star backward in time, the results stunned researchers. The calculations showed with high certainty that 70,000 years ago, Schultz's star passed just 0.8 light-years from our Sun. That distance equals roughly 5 trillion miles, which might sound like a massive gap in everyday terms on Earth. In the vast scale of astronomy, 0.8 light-years is an extraordinarily close encounter that put the star right in our backyard. More importantly, 0.8 light-years placed Schultz's star directly inside the outer region of our solar system's Oort Cloud. Schultz's star did not just pass near our solar system, it literally entered our outer home and plowed straight through our cloud of icy rocks. It was the closest known star flyby in the entire history of human existence on this planet. It proved that our solar system is not a closed fortress, but an open world, accessible to outside visitors traveling through the galaxy. Why does this giant gap between what scientists expected and what actually happened matter so much for our understanding of life on Earth? It matters because a star traveling through the Oort cloud acts like a massive gravitational magnet pulling on millions of fragile, icy bodies. Even a small red dwarf star carries enough gravity to twist, bend, and disrupt the orbits of ancient comets floating in space. If those disturbed comets get launched toward the inner solar system, they create a planetary hazard that could threaten the survival of living species. Have you ever wondered what would happen to human civilization if a giant comet suddenly emerged from deep space on a collision course with Earth? Share your thoughts in the comments section below, and make sure to subscribe to the channel so you never miss another deep dive into real space history. To figure out how dangerous this ancient encounter really was, scientists had to analyze the exact physical properties of Schultz's star. They needed to know its precise mass, its trajectory, and most importantly, how fast it was moving as it crossed through the Oort cloud. The speed of a passing star is one of the most critical factors in determining how much gravitational damage it inflicts on surrounding objects. If a star moves very slowly through an icy cloud, its gravity has a long time to pull on individual comets and disrupt their paths. A slow-moving star acts like a heavy tractor slowly driving through a dirt field, leaving deep ruts and tearing up everything in its path. On the other hand, if a star moves at extremely high speeds, its gravitational pull acts on surrounding objects for only a brief moment. In that case, the star passes by so quickly that most objects only receive a small gravitational nudge rather than a total orbital collapse. The fate of Earth 70,000 years ago depended entirely on the speed at which Schultz's star entered our neighborhood. Fortunately for early humans and for the future of our planet, Schultz's star was traveling through space at a remarkably high speed. It zoomed through the outer boundary of the Oort Cloud at roughly 180,000 miles per hour relative to our Sun. That high velocity limited the total time the binary system spent inside our solar system to just a few thousand years. Because it moved so fast and possessed a small mass, its gravitational disruption was far less destructive than it could have been. Before astronomers completed these precise speed calculations, many experts feared that any star entering the Oort Cloud would cause an instant disaster. They worried that a stellar flyby would immediately trigger a massive avalanche of giant icy comets falling toward the inner planets. They assumed that an invading star would shower Earth with constant impacts, causing rapid mass extinctions and destroying fragile ecosystems. That terrifying idea kept scientists searching through geological records for sudden impact craters tied to ancient star movements. What the actual mathematical models revealed was a much more complex and surprising physical reality than a sudden space catastrophe. The calculations proved that while a passing star does alter comet orbits, those comets take millions of years to fall toward the Sun. The Oort Cloud is located so far away from Earth that an object knocked inward moves across trillions of miles at a slow, gradual pace. It takes a long time for a disturbed icy rock to fall from the outer edge of space into the warm region where Earth orbits. This means that if Schultz's star launched a swarm of comets toward the inner planets, those comets are still traveling toward us right now. They are falling through the dark space between the outer boundary of the Oort Cloud and the inner planets where we live. We might not experience the full results of that ancient star's passage for another 1 or 2 million years into the future. The flyby was not an immediate explosion of danger, but rather a slow-motion timer set off in the outer depths of our cosmic backyard. To find physical proof that this event really happened, astronomers began searching for comets that show signs of being pushed by Schultz's star. They looked for comets with strange, unusual orbits that point back to the exact region of space where the star passed 70,000 years ago. By analyzing orbital data from thousands of known comets, researchers discovered a distinct group of nearly 30 long-period comets. These comets possess skewed, elongated orbits that match the exact gravitational footprint left behind by the passage of Schultz's star. These 30 comets serve as real, physical evidence lingering in deep space, like tracks left behind in soft mud after a traveler walks by. Their orbits were bent and reshaped by the gravity of the passing red dwarf as it sliced through the outer cloud. They provide clear proof that the mathematical models were completely accurate, and that an outside star really did invade our solar system. Scientists can trace these orbital paths back thousands of years to reconstruct the exact moment the two star systems crossed paths. Does it amaze you that astronomers can identify individual comets affected by a star that passed by 70,000 years ago? Drop a comment with your reaction right now, and make sure to hit the like button if you appreciate how detailed modern astronomy research can be. The impact of Schultz's star did not stop with distant comets floating on the dark edge of the Oort Cloud. Astronomers began investigating whether passing stars could also explain mysterious phenomena observed closer to home in the outer Kuiper belt. Far beyond Neptune, scientists have discovered several strange dwarf planets that orbit our Sun in weird, highly tilted, and stretched out loops. The most famous example of these unusual worlds is a dwarf planet named Sedna, which was discovered back in 2003. Sedna follows an extremely elongated orbit that takes more than 11,000 years to complete a single trip around our Sun. At its closest point to the Sun, Sedna is still more than 70 times farther away from us than Earth is today. At its farthest point, Sedna travels out to nearly 900 times Earth's distance, reaching into the deep darkness of space. Sedna's orbit is so distant that it never comes close enough to giant planets like Neptune or Jupiter to be pulled by their gravity. For many years, scientists expected that only a massive hidden world could explain why Sedna and similar objects have such weird orbits. Mainstream astronomers proposed that an undiscovered planet, often referred to as Planet 9, was hiding far beyond the orbit of Pluto. They believed that this heavy planet was using its strong gravitational pull to slowly shepherd distant icy worlds into stretched-out orbits over billions of years. A huge amount of observational effort was directed toward searching the dark outer sky for this mysterious missing world. However, recent scientific models have shown that ancient star flybys like the passage of Schultz's star offer a completely alternative explanation. When an outside star cuts through the outer solar system, its gravity can easily tug on distant dwarf planets like Sedna. A single close pass by a star can pull an object out of a round orbit and stretch it into a long, tilted loop. This means that some of the weirdest orbits on the edge of our solar system might not be caused by a hidden planet at all. Instead, those strange orbital shapes could be ancient souvenirs left behind by passing stars that visited our solar system long ago. This gap between the hidden planet theory and the stellar flyby theory highlights how much we still have to learn about our solar system. It demonstrates that our cosmic neighborhood is a dynamic environment shaped by both internal planets and outside interstellar visitors. Every unusual object on the edge of deep space tells a piece of a giant story that spans billions of years of galactic history. To make this ancient event feel even more immediate and real, we have to imagine what was happening on Earth 70,000 years ago. During this epoch, early Homo sapiens were sharing the planet with other human species, including Neanderthals and Denisovans. Our ancestors lived in small hunter-gatherer groups, huddling around open campfires under vast, unpolluted night skies. They relied on the stars for navigation, seasonal tracking, and storytelling, observing every shift and pattern in the sky above. Would these early human species have seen any visual evidence that an alien star system was passing through their solar system? Under normal conditions, a small red dwarf star located 0.8 light-years away would be far too faint to see with human eyes. Red dwarf stars produce very little visible light, and at 5 trillion miles away, Schultz's star would normally be completely invisible in the dark. Scientists originally assumed that the entire flyby passed in total darkness, completely unnoticed by any living creature on the surface of Earth. However, modern observations of red dwarf stars have revealed a violent stellar behavior that completely changes this picture. Red dwarf stars are notorious for having intense, powerful magnetic fields that generate massive atmospheric explosions known as stellar flares. During a major flare event, a red dwarf star can release thousands of times more light and energy than it normally produces. These explosive flare-ups can transform a dim, invisible star into a brightly glowing point of light within a matter of minutes. Astronomers calculate that Schultz's star likely experienced frequent, powerful magnetic flares while it was passing through our outer Oort cloud. During these major flare episodes, the star would have suddenly flashed into visibility in the night sky above Earth. For hours or even days at a time, ancient humans looking up into the dark sky would have seen a mysterious reddish star appear out of nowhere. It would have glowed among the familiar constellations before slowly fading back into the deep, dark void of space. Imagine what early humans must have thought as they sat around their campfires, watching a strange red star light up in the sky. They had no scientific tools, no telescopes, and no understanding of gravity or the vast structure of the Milky Way galaxy. To them, this sudden red visitor would have seemed like a powerful omen, a spiritual sign, or an incredible mystery in the heavens. They watched an invading sun cut through their solar system without ever knowing the true cosmic story taking place above their heads. What do you think early humans thought when they saw a red star suddenly flash in the ancient sky 70,000 years ago? If you enjoy imagining these incredible historical moments, leave a comment with your thoughts below, and drop a quick like on the video right now. The discovery of Schultz's star inspired scientists to look even deeper into the movement of stars throughout our region of the Milky Way galaxy. Researchers realized that if one star invaded our outer solar system 70,000 years ago, many others must have visited us over time. They began asking fundamental questions about how often these cosmic close calls occur and what they mean for the long-term safety of Earth. To answer these questions, astronomers needed a far more powerful tool to map the positions and velocities of stars across space. That tool arrived in 2013, when the European Space Agency launched a revolutionary space telescope named Gaia. Gaia was designed with one primary mission: to create the most accurate three-dimensional map of our galaxy ever produced by human technology. The spacecraft sits far from Earth, using ultra-precise cameras to measure the distance, position, and movement of over 1 billion stars. Gaia tracks how fast stars are moving toward or away from us, as well as how they shift across the sky over multiple years. Before Gaia was launched, astronomers possessed accurate tracking data for only a tiny fraction of the stars in our local galactic neighborhood. Their historical calculations were limited by large margins of error, making it difficult to trace past star paths with total confidence. Many ancient flybys remained completely hidden from scientific view because scientists simply did not have precise enough measurements. The arrival of Gaia data transformed astronomy, opening up a massive catalog of stellar movements that revealed our galaxy's true history. When scientists applied advanced computer algorithms to the massive Gaia datasets, they were able to track millions of star paths forward and backward. The results revealed that stellar flybys through our outer solar system are far more common than anyone had previously estimated. The data prove that a star passes close enough to penetrate our Oort cloud roughly once every 100,000 years. Over the 4.5 billion year lifetime of our solar system, thousands of outside stars have sliced through our outer protective bubble. Some of those ancient visitors were much larger, heavier, and more powerful than the tiny binary system of Schultz's star. Imagine a massive star, several times heavier than our Sun, cutting directly through the dense inner region of the Oort cloud millions of years ago. Such a heavy star would unleash massive gravitational disruption, ripping millions of icy bodies out of their orbits and scattering them across space. An event like that would launch a devastating comet storm that could last for millions of years in the inner solar system. This shifting perspective provides fresh insights into one of the biggest mysteries in Earth's geological history: mass extinction events. Geologists and paleontologists have long noted that major biological extinctions on Earth seem to occur in rough cycles every 20 to 30 million years. Scientists have debated for decades whether an astronomical mechanism could be driving these periodic waves of destruction across our planet. The regular passage of heavy stars through our Oort cloud offers a compelling astronomical trigger that aligns with these ancient impact cycles. When a massive star disturbs the inner Oort cloud, it sets off a long-term gravitational chain reaction that eventually reaches the inner planets. Millions of years after the star has moved away, a high-density stream of giant comets begins crossing the orbits of Earth and Mars. If Earth suffers multiple large comet impacts over a short period, the environmental consequences can be catastrophic for global life. Giant impacts throw huge clouds of dust and soot into the high atmosphere, blocking out sunlight and causing global freezing conditions. These impact winter conditions destroy plant life, collapse food chains, and lead to the widespread extinction of dominant animal species across the world. The legendary impact that wiped out the non-avian dinosaurs 66 million years ago may have been part of an ancient comet storm. That devastating impactor might have been set on its fatal path by a passing star that sliced through our Oort cloud millions of years earlier. Our planet's biological history has been shaped repeatedly by the gravitational hand of outside stars passing through our solar system. We are not just talking about ancient history that happened millions of years in the past when dinosaurs walked the Earth. The exact same galactic dynamics are happening right now as our Sun continues its continuous orbit around the center of the Milky Way. Space is an active, evolving environment, and modern astronomers have already identified the next major star heading straight toward our cosmic backyard. Using the latest Gaia tracking data, scientists have mapped the exact trajectory of a nearby star that will make a terrifyingly close pass in the future. The star is named Gliese 710, a glowing orange dwarf star currently located about 63 light-years away from Earth in the constellation Serpens. Gliese 710 is much larger and heavier than Schultz's star, possessing about 60% of the total mass of our Sun. It is currently moving through space on an almost direct collision course with our solar system, traveling toward us at extreme speeds. Astronomers have been tracking this star for years, continually refining their calculations as new orbital data becomes available. Scientists originally expected that Gliese 710 would pass at a safe distance of several light-years away from our Sun. Early measurements suggested that the star would give our solar system a wide berth, causing no major gravitational disturbance to our outer cloud. Mainstream astronomers felt confident that Gliese 710 was just another distant neighbor passing by peacefully without touching our territory. That expectation allowed people to view the approaching star as nothing more than an interesting astronomical footnote for the distant future. When researchers analyzed the newest, most precise data release from the Gaia satellite, those comfortable expectations were shattered. The updated calculations revealed that Gliese 710 is heading far closer to us than anyone had previously calculated in earlier studies. In about 1.3 million years, Gliese 710 will pass just 0.16 light-years from our Sun. That distance equals roughly 900 billion miles, placing the star deep inside the dense inner region of our Oort cloud. 0.16 light-years is nearly 5 times closer than Schultz's star came during its passage 70,000 years ago. Gliese 710 will not just graze the outer edge of our solar system, it will slice right through the heart of our icy defense shield. Because Gliese 710 is much heavier than Schultz's star and will pass much closer, its gravitational impact will be far more intense and widespread. Computer models indicate that Gliese 710 will disrupt the orbits of millions of icy bodies, triggering a massive, long-lasting comet shower. When Gliese 710 reaches its closest point to Earth, it will be an incredible spectacle in our planet's night sky. It will shine brighter than any other star or planet visible from Earth, glowing with a fierce, brilliant orange light. For thousands of years, it will dominate the night sky, moving visibly across the constellations as it travels through our Oort Cloud. Whatever species lives on Earth 1.3 million years from now will look up at a sky completely transformed by this bright stellar visitor. The approaching pass of Gliese 710 proves that our solar system is in constant physical contact with the rest of the galaxy. It highlights the importance of studying stellar flybys so that future generations can prepare for the hazards of long-term comet showers. By tracking star paths today, scientists are building a comprehensive map of future space risks that could impact Earth over millions of years. We are learning that planetary defense requires watching not just nearby asteroids, but also full star systems moving across the galaxy. Could you imagine living on an Earth where a glowing orange star dominates the night sky while comets fall toward the inner planets? Tell me what you think future intelligent life on Earth will do when Gliese 710 arrives, and drop a quick like on this video if you find this incredible. Understanding these ancient and future star flybys forces us to zoom out and re-examine our own place in the universe with fresh perspective. We often go through our daily lives assuming that Earth is a completely safe, permanent sanctuary isolated from the rest of space. We focus on immediate, short-term concerns while forgetting that our homeworld is an active participant in a vast, dynamic galaxy. The story of Schultz's star proves that our solar system has survived dramatic near misses that could have easily altered the history of life. Every human being alive today exists because our planet survived a series of incredible cosmic coincidences over millions of years. If Schultz's star had been moving slightly slower, or if it had possessed a slightly larger mass, the story of human evolution might have ended early. A massive comet storm 70,000 years ago could have wiped out our ancient ancestors during a fragile moment in human history. Our entire modern world, with all its technology, culture, and achievements, stands on the foundation of cosmic luck. These scientific discoveries reveal that space is an interconnected community where events light years away can directly affect our world. We are not isolated observers watching space from a safe distance. We are traveling through the Milky Way on a gigantic natural spaceship. The stars we see shining in the night sky are not fixed lights, but fellow travelers moving along their own dynamic paths across space. Occasionally, those paths intersect with ours, leaving physical evidence in the orbits of comets and changing the course of planetary history. As our observational technology continues to advance, we are gaining the ability to map these interstellar events with unprecedented clarity. Powerful space telescopes and advanced computer simulations allow us to look back millions of years into the past and far into the future. We are unlocking the true story of how our solar system interacts with the galaxy, transforming dark mysteries into clear scientific understanding. By studying the past of Schultz's star, we are learning how to protect our world and ensure the long-term survival of human civilization. The proof that Earth survived a near miss with a rogue star is a testament to the incredible power and mystery of our universe. It reminds us that our cosmic neighborhood is full of deep secrets waiting to be uncovered by curious minds willing to look closely at the data. Every comet floating on the edge of space, every strange orbit in the Kuiper Belt, and every distant star carries a piece of our shared story. When we look up at the night sky, we are looking at an ongoing adventure that has been unfolding for billions of years. If you found this deep dive into our solar system's wild history fascinating, please hit the subscribe button right now and turn on all post notifications. By joining our channel, you will be the first to explore groundbreaking space discoveries, real scientific mysteries, and incredible cosmic stories every week. Drop a comment below answering this question. Do you think humanity will develop the technology needed to deflect incoming Oort Cloud comets before Gliese 710 arrives in 1.3 million years? I want to hear your thoughts, theories, and predictions, so let us start a conversation in the comments section down below. Also, take a moment to share this video with your friends, family, or anyone you know who loves space, science, and deep mysteries about our universe. Thank you so much for spending your time with us today. Keep looking up at the stars, and we will see you in the very next video.